Another important topic for the discussion is sex-linked inheritance, and one of the important characteristics of this would be that one of the sexes or one of the sex would be disproportionately affected as compared to the other sex. So, for example, more males will be affected compared with the females, or more females will be affected compared with the male. So let's look into the three patterns. So it's either X-linked recessive, or it would be X-linked dominant, or it would be Y-linked genes. So let's dive into the discussion over here. So let's start off with X-linked recessive, and one of the example here would be color blindness. So let's make use of that as our example. So what would be the notation that we'll be using? Of course, we will make use of the X to symbolize that it will be found on the X chromosome. And since it is recessive, this means that we will make use of the small letter or the recessive, which would be the one that has the disease or the phenotype in focus. So the normal dominant will be X big N, which is the normal. The colorblind, as our example, would be the recessive, and this will be symbolized by X small n. Given those notations, we can have three possible combinations for females: X big N, X big N, X big N, X small n, and X small n and X small n. So X, the first one would be female with normal eyesight. The second one would be female with normal eyesight but a carrier, while the third one would be female with color blindness, because they have this female will have both recessive on the X on her X chromosome. In terms of the male, there are two possible genotypes, X big and Y, X small and Y, which would be the first one would be male with normal eyesight, while the X small and Y would be male with color blindness, or the recessive allele, recessive disease. So with this, we can imagine crosses of a male and a female, and let's look at the possible um, results or descriptions of their children. So for example, we have here a male who is affected, thereby if he is affected, he is X small and Y, the recessive allele would be found on his X chromosome, while the female, let us say that she is a carrier, so X big N and X small n. So then she's a carrier, therefore she is still phenotypically normal, but she is carrying the disease allele. So let's look at the possible children. So combining the first with the first letter of the male and the female, we have X big and X small n. The first and the second will be X small n, X small n. The third, which is the Y, and the first X chromosome with the female is X big and Y, while the last is the Y from the male and the X small n from the female, X small and Y. So let's look at the phenotype. The first one would be normal female, but she is a carrier, still normal. Colorblind female will be the second. How about the next one? The next one would be normal male, and the last one would be colorblind male. So a cross between an affected or colorblind male with a carrier female will produce two colorblind children out of four children, which is one half, which is 50%. But if we're going to be asking what would be the chance or the percentage that a female colorblind daughter, or a colorblind daughter will be produced, or a colorblind daughter will be birthed. So we have here one female who is normal but carrier, and one female who would be a colorblind. So it's one out of two females, so it's 50%. While the male, there will be one male out of two males who will be colorblind, so there will be a 50% chance of colorblind males. So that is the result of such a cross. How about the situation where the male is normal while the female is carrier for color blindness? So let's see the crosses. The first and the first will be crossed, and you have an X big N, X big N. The second, first and the second letter, or the second X chromosome of the female will be crossed. You have an X big N, X small n. You have a Y from the male and the X big N from the female, X big N Y, and the Y from the male and X small n from the female. So the first child would be a normal female. The second child would be a normal female but carrier. The third child is a normal male, while the last child would be a colorblind male. So counting the number of normal and counting the number of colorblind child, you will have one colorblind child out of 4 children, which would be 25%. However, if the question would be how many of the uh, female would be a carrier, that will be 100% because both of them would be normal. And if the question would be how many percent will the couple have a colorblind son, then the answer would be 1 out of 2 males would be colorblind, and that would be 50%. So depending on the question, you have to really analyze. So that will be the result of such a cross. Another cross is, how about if the male is normal while the female is colorblind? So this means that the female will be X small and X small, and crossing the first and the first, you will have an X big and X small, and first and the second will be an X big and X small n, and the Y will be given by the father and X small n by the mother, X small n Y, and the Y and the X small n Y. So you have all of this. So the first child will be a normal female but carrier. Second is a normal female but carrier. Third is a colorblind male, while the last one is a colorblind male. So you will notice here that 2 out of 4 children are colorblind. But looking at the males, there will be 100% males colorblind, while 0% of the females would be colorblind, though both of them would be carriers. So that will be the result of such a cross if a normal male is crossed with an colorblind or an affected female. Okay, so that would be it. So again, colorblind is an example of sex-linked recessive, while the Duchenne muscular dystrophy, wherein the muscles are becoming wasted, is an example also of sex-linked or X-linked recessive. Let's now proceed with X-linked dominant. In this case, it is the dominant allele that would be producing the disease, which means that our notation will change. The X big N will now be the one that is diseased, while the normal recessive would be X small n. With this, we have possible combination for the female. We have X big N, X big N, X big N small n, and X small n small n. So in this case, the X big N would be a female with disease. X big N small n, the heterozygote, will still be a female with disease because you only need one uh, dominant allele to produce the disease, and then you have there the X small n, which will be a normal female. How about the males? Well, you have this, so the X big N Y will be a male with disease, while the X small n Y will be a normal male. Now let's look at the possible crosses in the children that can be produced. If you are a male that is affected X big and Y, and then the female is a heterozygote X big and X small y, what will be the percent of their children that will have the disease? So let's combine the first and the first. You have an X big and X big N. First and second, X big and small n. The Y given by the male, X big and Y, and the Y given by the male and the X small n coming from the mom, X small and Y. So the first child is an affected female, second child is an affected female, the third is affected male, and the last one is a normal male. So in this case, we have, instead of just one affected, we have 3 affected out of 4, and that should have been 75%. But if the question is how many would be normal, that will be 1 out of 4 children, and that will be 25% normal child or normal children. So you will be having this kind of combinations or percentages with this kind of cross between an affected male and a heterozygote affected female. Okay, and now of course, if you take note of the males only, 50% of the males will be affected, while all of the females, 100%, will be affected. How about if the cross is between a normal male and a heterozygote affected female? So in this case, the X-linked dominant will have this kind of crosses. First and first, you have an X big and X small n. First and second, it's an X small n, X small n. Y coming from the dad, X big N Y, and the Y coming from the dad, X small n Y. So the first would be affected female because you only need one dominant allele to show the phenotype or the disease. Eh, Second is a normal female, both recessive. The third is an affected male, and the last one is a normal male because of the recessive X small n. So in this case, you will have here two affected children, so that will be the answer is 50%. If you're talking about only females, you will have 50% females affected. If males only, 50% males would be affected. So those are the possible crosses, children, and percentages of their phenotypes with such a cross. Okay, last one. How about a male normal and a homozygous affected female, X big and X big N? So you will have this. You will have this as well. Heterozygote, you have X big and Y and X big and Y. So you will have affected female, affected female, affected male, affected male. So all of them will be affected. Okay, 100% of them will be affected because of the X chromosome coming from the female, both of which would be affected. Okay, Okay, example of X-linked dominant would be Enconthia pigmenti. Another one is vitamin D resistant rickets, which is hypophosphatemic rickets. So that is an example of X-linked dominant. Okay, last but not the least is Y-linked, and this is very easy because Y-link is only found in the Y chromosome. So we would be expecting that only males will be affected by this one because only males will be carrying the Y chromosome. So in this case, we can make use of a notation like XYD, XY. So the normal male doesn't have the affected Y chromosome, while the male with the affected Y chromosome will have the disease or the phenotype in focus. If the male is affected, where the Y chromosome contains the affected allele, then you can have this combination. First of all, the female, another female, and here's the male, XYD, and XYD. So all the male females will be unaffected because the Y chromosome is the one that is affected, while all the males will be affected because, as I mentioned a while ago, it is the Y chromosome that is only found in males that would be containing the disease allele. So that would be 100% females would be normal, 100% males would be affected. Okay, here's an example of the Y-linked disease. So you have the web foot, the porcupine man, where there would be a number of scaly the scaly skin would there will be some protrusion and skin will thicken, and then you also have here the hypertrichosis in males. So all of these are example of Y-linked diseases. Okay, let's look at some concepts. Let's answer some questions. Why are males more often affected by sex-linked traits than females? We have answered this beforehand. Male hormones such as testosterone often alter the effects of mutation on the X chromosome. Female hormones such as estrogen often compensate for the effect of mutation. X chromosome in males generally have more mutations than females, or males are hemizygous. The answer to that is males are hemizygous because there would be no other X chromosome that could possibly mask the effect of the allele that would be containing the which is diseased or which is the abnormal allele, especially in the sex-linked recessive. So since males only have one X chromosome, if they have uh, the the diseased allele, then they won't be able to mask it. Okay, Number two, red-green color blindness is a sex-linked recessive trait in humans. Two people with normal color vision have colorblind son. What are the genotypes of the parent? So the parents would be normal. So since color blindness is an X-linked recessive disease, so that will be X small n. That will be containing the color X small c, I mean, that will be containing the X small n here will be containing the color blindness. So the male does not have any color blindness or normal color vision, therefore he doesn't have the allele. It's X big and Y. And then the mom, who is also phenotypically normal, since two people with normal color vision, so this means that it has one, the female is a carrier, X big and X small n, because she is phenotypically uh, normal, but their child is colorblind. So the X small n will combine with the Y to produce that colorblind son. So the answer to this one is letter D. Okay, another one. A woman heterozygous for color blindness marries a colorblind man. What would be the ratio of carrier daughters, colorblind daughters, normal son, and colorblind sons in the F1 generation? So first of all, woman is heterozygous, which means she is a carrier. So this will be X big C, X small c, while the male would be a colorblind, so one of his X chromosome would be affected. So in this case, the X, which is symbolized by the red, is affected, while the woman or the mother is a carrier, so one of her X chromosome is affected. So combining in the Punnett square, you will see that that the female is a carrier because she has one that is not affected. The male is normal. The female is affected because both of these would be recessive, and the female is affected because his X chromosome is affected. So you have your 1:1:1:1 ratio, or 1/4, 1/4, 1/4, 1/4. One of this would be a female who is affected, the other is a female who is unaffected, one is a male who is unaffected, while the other is affected. So the answer is letter C. Okay, another example, a normal male mates with a female who is a carrier for an X-linked recessive disorder. Of the offspring that they may have, it is probable that. So what's the correct answer here? Let's try to analyze first. So normal male mates with a female who is a carrier. So you have here that if the male is normal, we would expect it to have a dominant allele on the X chromosome. While the female is a carrier, so she will have a normal allele on one X chromosome and an abnormal allele on another chromosome. So in this case, the male will have normal X and Y, while the female has one normal X and one abnormal X. Combining them together, normal female, normal male, abnormal carrier female, and then abnormal male. So the answer to that would be one half of the sons will be affected, and one half of the daughters will be carriers. So that would be the answer. It's letter E.